according to the 7th National Development Plan document in 2015. Zambia's demand for electricity stood at 1,949 megawatts. However, the sector was only able to produce 1,281 megawatts, thus giving a deficit of 668 megawatts.
In a long time now, we haven't been undertaking huge projects as Zambians, as well as just as a region. The last big project we undertook as a country in terms of the construction of power plant was the Kafue Gorge upper, whose last machine we commissioned in 1978. Then the next project was commissioned in December 2012. So between 1978 and 2012, we did not undertake any project. So obviously, that's why we find ourselves in such a situation, because population has been growing, the economy has been growing, and so on and so forth. And the only project we commissioned was just a 1 megawatt plant, which is the Shiwangandu power station. And then thereafter, following year, we did the Kariba North extension, which we added at least 360 megawatts. We went on to do in 2015 Iteshi. We added another 120 megawatts.
Since 2004, this project has been on and off, from management, from the board, from the ministry, from the presidency. I don't know why. Until we made that board decision in 2015 to launch it as Zambia's first major investment in power in more than 50 years. And I'm very proud of that.
So we are so excited that this huge project will bring along a lot of benefits, because the situation currently that we are experiencing is not only bad for our esteemed clients, but it's also bad for ZESCO.
Hydropower or water power is power derived from the energy of falling water or fast-running water, which may be harnessed for useful purposes. Since ancient times, hydropower from many kinds of waterfalls has been used as a renewable energy source for irrigation and the operation of various mechanical devices. ZESCO, Zambia's main power utility, has embarked on the development of the Kafue Gorge Lower Hydropower Project, KGL-HPP. The project includes the construction of a 140-meter-high concrete face rock-filled dam, CFRD, with a crest between 8 meters and 10 meters and a length of approximately 378 meters.
我们有信心按期完成这座赞比亚最高的大坝。
Looking forward to the future, we are to take a heavy burden and embark on a long road in the 18 months to come. A total of 1,600,000 cubic meters of concrete are to be placed. Although we are facing a tight schedule and various challenges, we firmly believe that we will complete the highest dam in Zambia without delay, with deep trust and tremendous support from Sano Hydro seniors, Zambian government, ZESCO, KGL, consultant, and our 3,500 Chinese and Zambian employees. Happiness is always achieved through hard work. Let us work hard hand in hand to create a better tomorrow, and allow me to wish a successful placement of concrete in the first block of our RCC dam. Thank you.
Today, on the 6th June, we have started with the RCC dam. You can see in the background they are placing the first layer RCC. That is done first we place slurry, that is a cement water mixer on the surface, and then we push by dozer the RCC over. We place that in a 30 centimeter thick layer, first with the dozer, and afterwards we will compact that with the big roller, which are not yet on the RCC. So we hope that today we have at least one whole length placed, maybe even more.
Since the Kafue Gorge Lower Hydropower project commenced in 2018, notable progress has been made with visible changes occurring on a daily basis.
A lot of work has been carried out. Our dam wall will be quite high, at about 139 meters high. And we started our excavation from scratch, cutting back the mountain sides and the riverbed. And from June 2018, we started the placement of concrete.
The dam wall has seen substantial progress in terms of construction. At the moment, currently we are at 80% in terms of construction. And going forward, we are seeing ourselves completing this infrastructure in the first quarter of next year.
581 meters above sea level, that's where the crest of the dam is designed to be. We haven't reached there yet, but as we finish, that will be the crest elevation. So that 130 meters is from the foundation, which is at 450.5 meters above sea level to 581 meters above sea level as dam crest. At the bottom, we have a width which is in line with the flow of the river of 125 meters. And the length, apparently the length is shorter because the valley is narrower at the bottom. The length is 30.5 meters. As we go up, the length is increasing, whereas the width is narrowing because the dam faces, both upstream and downstream, are inclining upwards as we go up. So on the dam crest, we have a width of 8 meters, and the length will be 374.5 meters. We expect to finish placement of RCC in the month of November this year, and the overflow section, plus casting of CVC. We are planning that by end of January we should be done, because going by the schedule, it's planned that in March we should start pounding the reservoir in readiness to commission the first unit in April. We have what we are calling an environmental flow pipe, which we've already started embedding in the dam body. Right now it's protruding at the elbow point, and that will come all the way to the mini hydro. Why it's coming to the mini hydro? It's to further utilize this environmental flow. By the requirement that has been put onto KGL through ZEMA, we have to have 11 cubic meters per second of this environmental flow. So it's been designed that 11 cubic meters per second, before it finally flows back to the river, it has to pass through the mini hydro, where we are going to have 2 units of 6 megawatts each. So with that environmental flow of 11 cubic meters per second, we'll be able to generate 12 megawatts.
The dam wall is but one of the many elements of the hydropower plant. Progress elsewhere on site has equally been taking place.
In the Powerhouse, we've also done a lot of work. Our initial works were in terms of civil works, mainly excavation and the concrete lining of the powerhouse. Our powerhouse is partially surface. The lower parts are, of course, excavated into rock. We've finished all that. Construction of the outer outlines of the powerhouse have been completed. We've roofed the powerhouse, and now our works have concentrated right inside the powerhouse for installation of the units. So we've started the actual installation of the turbine generator units with the draft tubes on all the 5 units already installed and embedded in concrete, because those structures that we embed in concrete. On Unit 1 and Unit number 2, we've moved further. We've put in the spiral casings and embedded those in concrete as well. And now we are working upwards towards the generator.
Belt conveyors are used to transfer concrete horizontally and limited distances vertically. Conveyors made expressly for handling concrete are relatively inexpensive and may eliminate the need for other more expensive auxiliary equipment such as cranes. They are particularly useful in areas such as tunnels, where space is limited, and are widely used on building construction, especially large floor slabs and bridge decks. In massive construction such as mat foundations, dams and power plants, which require large quantities of concrete, conveyors are advantageous because of their placing capacities. Economy can be achieved through use of belt conveyor systems because the operating crew can be small in relation to the high rate of transport that is possible. Transformers, sometimes called voltage transformers, are devices used in electrical circuits to change the voltage of electricity flowing in the circuit. Transformers can be used either to increase the voltage, that is, stepping up, or decrease the voltage, otherwise known as stepping down. Energy is lost in the process of transmitting electricity long distances, such as during the journey from a power plant to homes. Less energy is lost if the voltage is very high, so electrical companies like ZESCO use high voltage in long-distance transmission wires. However, this high voltage is too dangerous for home use. Thus, transformers are used to change the voltage of electricity as it travels from the power plant to homes. First, the voltage of electricity coming from the power plant is stepped up, using transformers to the right level for long-distance transmission. Later, the voltage is stepped down before it enters homes, once again using transformers.
Kafue Gorge Lower Hydropower Project will have 5 generating units, each rated 150 megawatts. Now, each of the generators will be connected to a generator transformer, and these are the generator transformers which have started arriving. We'll be generating at 13.8 kilovolts, and we need to transmit this power to the national grid at a higher voltage. So for us to be able to do that, this is the key, the transformers. They are rated 13.8 to 330 kV and 187 MVA. We are now unloading the transformers, bringing them to their respective transformer cells. We call them transformer cells. And this is a cell for transformer number 5 or generator transformer number 5 coming from generator number 5. As you can see on my left, there are 4 more cells in which each of the other transformers will be housed. And you may be interested to know each of the cells is separated from the other using a wall, what we call a firewall. The whole concept or idea is that In case of fire, because these transformers will be at high voltage and the current is also high, and they will be filled with oil. In case of fire on any of the transformers, it shouldn't escalate to the next transformer. The other transformer is isolated from the one before it, using the fire oil. So basically, that's the concept of what this project, in terms of scope of the transformer works, is all about. Once we get power from the generators at 13.8 kV, we'll transform it to 330 kV, and from the 330 kV HV or HV side, we'll run 330 kV cables through this cable gallery you are seeing in front of me, and the cables will run up to the switchyard, which we will call the gas insulated switchyard. It is from the switchyard that now we'll be able to convey the power to the national grid through the transmission line.
The Kafue Gorge Lower Power Station will be the third largest power station in the nation when it is finally commissioned, coming in at 750 megawatts. You may wish to know that we already have Kariba North Bank, which is essentially a combined power station. It's 2-in-1. We have the original power station, which is just called Kariba North Bank Power Station, and then there is the extension, which brought in an extra 360 megawatts, which brings us to a total of 1,020. Then we have the Kafue Gorge Upper, which during the recent rehabilitation was also upgraded from 900 megawatts to 990 megawatts. So when you look at the other power stations, we have Victoria Falls Power Station, which is currently around 188 megawatts. It's currently the third largest. But when we bring in the Kafue Gorge Lower, it will be bringing in 720, which is a massive boost. And with respect to our economic trajectory, you may wish to know that we have to match in tandem with the rest of the nation.
The Kafue Gorge Lower Hydropower Project is truly a worthwhile project. Apart from just mitigating the future demand for power in the country, the project has positively contributed to the development and transfer of valuable skills to the Zambian professionals, both at technical and project management levels.
It's a privilege for me to be part of this, because, like I said, between 1978 and 2012, no such projects were being undertaken, meaning that the engineers were essentially maintenance engineers. They were just maintaining existing infrastructure. But I think all I can say is to say we thank God that we're part of this, and we're able to construct power plants, meaning that our engineers and everyone else who's involved, they're getting more knowledge. Thereby, once all this infrastructure is completed, they fully understand, and they're able to maintain this with full knowledge. This is a very worthwhile project. Number one, the power station is not standalone along the Kafue River. It is a cascade of 3 power plants. We have on the upstream the Iteshiteshi, Then the next is the Kafue Gorge Upper, and obviously the current one that we are talking about, the Kafue Gorge Lower. What this does is that then you are going to have 3 reservoirs along one river. The reservoirs are there for banking. You are able to bank your water. And you find that it is easier to operate when you have more reservoirs or storage of water in one river. Obviously, nowadays we have challenges of climate change. We are mindful that we need to have a mix in terms of our power sources. That brings us to the point number 2, that we're not only looking at hydro as ZESCO. We are also looking at solar. We are already in partnership with a Moroccan company called Massen, where we are doing a project in Serenge for solar. And this project is about 200 megawatts. We are also undertaking another project in wind with the same company with a capacity of about 150 megawatts. And on our reservoirs, we're trying to put up solar plants on the reservoirs. So the reservoirs in question, Kariba, on the Kariba we'll have a solar plant. In Teshteji we'll have a solar plant. On the newly created reservoir, once we complete, we'll have a solar plant. Our intention actually for the Kafue Gorge Lower is to commission this solar plant by the time we're completing our project. We intend to have about 200 megawatts of solar on Kafue Gorge Lower, 200 megawatts of solar on Kariba, and 100 megawatts on Iteshiteji.
ZESCO's vision for Zambia is to be the hub for power trading in the region by the year 2025. Because Zambia is uniquely placed, surrounded by 8 neighbors, the market for power is readily available. To take full advantage of this opportunity, the vision is to spearhead the effort of improving interconnection in the region, making power more affordable and accessible for all.